Hello, today we're going to talk about section 5-2, matrix solutions on linear systems. We're going to use something called the Gauss-Jordan method of solving a system of linear equations, as well as looking at some special systems. So there's several ways to solve a system of equations. You can graph them to see where the lines intersect if it was just two lines. You could do substitution, we can do elimination. But what if we get into bigger systems, say 3 equations and 3 unknowns? Well, we can solve those by using matrices. And to use matrices, we will look at the equations, we'll write them and keep them in order, where x's and y's and z's are together and your constants are together. And then we'll look at the coefficients only, and we can manipulate rows of numbers in order to solve a system. So it says, in this system, we will develop a method for solving linear systems using matrices. We start with a system and write the coefficients, the variables, and the constants as an augmented matrix of the system. So, excuse me. So the system here, we have 3 linear equations with 3 variables, and if you'll notice, the x's are together, the y's are together, the z's are together, and the constants are together on the other side of the equal sign there. If we look at just the coefficients of the first equation, the coefficient of my x is a 1, the coefficient of y is 3, the coefficient of z is 2, and of course my 1 is on the other side. And so we do that with all 3 equations, and each equation creates a row. And then, of course, we have my first column that represents my column of x's. The second column is a column of y's. The third column, my column of z coefficients. And, of course, this last row. And if you'll notice, right here, we have this little bar. What this is doing, it's called an augmented matrix because we actually have 2 matrices put together. We have our coefficient matrix here. This is the coefficients of my 3 equations. And then over here we have the solutions. So we took the coefficient matrix and the solution matrix, we put it together into one matrix and made an augmented matrix. When we're talking about matrices, and if some of the stuff repeats, you just get to hear it twice. When we're talking about matrix, we always talk about how many rows it has by the number of columns. So in this case, we have 3 rows and 4 columns. So this would be considered a 3 by 4 matrix. And it's just important that you understand where this is headed. Okay? The optional vertical line separates the coefficients from the constants with 3 rows and 4 columns. This matrix has a dimension of 3 by 4. The number of rows is always, always, always given first. Don't forget that. When I want to know about the dimensions of a matrix, how many rows by how many columns? Rows by columns. Matrix row transformations. For any augmented matrix of a system of linear equations, the following row transformations will result in a matrix of an equivalent system. Okay. So as we go through this, I'm going to talk a little bit about what's going on. Remember that each row of a matrix represents a different equation. So if I have 3 equations, does it really matter which equation comes first or second or third? The answer to that's no. So rule number 1 says if I'm dealing with an augmented matrix, I can interchange rows. So if I don't like the order of the rows, I want to rearrange it, just flip them. It's no big deal. Take one row, make it row 2. Take row 2, make it row 1. Take row 3, make it row 1. It doesn't matter. So that's rule number 1. Rule number 2, multiply or divide the elements of any row by a non-zero real number. So when we had an equation, if you were to take an equation and multiply both sides by 0, you have nothing. That's why it must be non-zero. If you take an equation and multiply it by 3, every single term is multiplied by 3. So though the equation looks different because we multiplied everything by the same number, it's essentially the same equation. And that's exactly what's taking place with number 2. You can multiply a row. Remember, each row represents an equation. It's not a big deal. And number 3, says replace any row of the matrix by the sum of the elements of that row and a multiple of the elements of another row. So what that is saying is if you take two equations and add them together, or two rows and add them together to replace one, that's acceptable. The Gauss-Jordan method. This is a systematic technique for applying matrix row transformations in an attempt to reduce a matrix to a diagonal form with ones along the diagonal for which the solutions are easily obtained. So if you'll notice in this 2 by 3 matrix, we have a 1 and a 1 here. That's your primary diagonal there. So that primary diagonal has ones in it, and if you'll notice, everything else on that left side is a 0. If we had a matrix with 3 equations, so we have a 3 by 4 matrix here, we still have ones on that primary diagonal. Everything else is 0. This is called reduced row echelon form. So when you're looking at your homework and stuff and starts doing some vocabulary stuff, reduced row echelon form has ones on the primary diagonal. Everything else is 0 on the left side. And then on the other side, your AB or ABC, if you have 3 equations, those are going to be the solutions for each of the variables. So our goal when working with matrices is to actually get the matrix into a reduced row echelon form, and this is just a method of solving the system of equations. So we're going to talk about using Gauss-Jordan method to make this happen. Step number 1, obtain 1 as the first element of the first column, and that's talking about this one. This is my first row, this is my first column. In Gauss-Jordan, I want to do whatever it takes, whether I'm doing row swaps, whether I'm combining different rows together, whatever it takes legally using those steps on the previous slide there, I want to make that first row, first column a 1. Step number 2, use that row, now that it's a 1, to make everything else in that column a 0. And once you finish doing that, you now have a 1 in the top, on the very top left, and then a 0, 0, or however many equations you have. Everything else is 0. Step number 3, get a 1 in the second entry in the second column. Okay, so go back one slide again. Once I have established a 1 in that first row and first column and made everything else 0, the next thing I want to do is I want to make this one a 1. And then I'm going to use that equation to make everything below it turn into a 0. That's what step 4 just says. Use the second row to transform the remaining entries in the second column to 0. And then we're going to continue this. So we could do this even if we had 10 equations and 10 unknowns. We could actually end up with a perfect diagonal of 1s. And then once we do that, we'll have our answers to each variable in that solution column. Solve the system. Okay, so we are going to use that method of Gauss-Jordan to solve this equation. So, are already in the same form. These are both happen to be in standard form. Notice I have my x's together in the column, I have my y's in a column, I have my equal sign lined up, and then on the right side I have my solution. Sorry about that, hit the wrong button. Okay, I can write this as a matrix. So to write this as a matrix, basically what we're doing is we're only paying attention to the numbers. So in that first row of numbers, I have a 3, I have a -4, and I have a 1. In my second equation, my x coefficient is a 5, my y coefficient is a 2, and my solution is 19. And then I'll put brackets around this to indicate that we're working with a matrix. And then again, this bar, it's not required. It just helps you to see that it is an augmented matrix and we've got it separated. So again, we have 2 rows. We have 3 columns, which means we have a 2 by 3 matrix. Okay, so we're going to go ahead and we're going to solve this guy. Let me go back. I just wanted to make sure I didn't have this next slide with anything on it. So to solve this, I want to make that 3 turn into a 1. Well, how can we do that? Or I can make the 5 a 1. So again, it doesn't matter which one you do. You just have to make a 1 in that first column. And if we have to do a row swap because we choose the second column, that's fine. To turn a 3 into a 1, I could multiply line 1 by 1/3. So if I took 1/3, I'm going to write it right here. If I took 1/3 and multiplied this entire first row by 1/3, what happens? Well, 3 times 1/3, or 3 divided by 3, is 1. Negative 4 times 1/3, or negative 4 divided by 3, is negative 4/3. 1/3 of 1, 1 divided by 3, is 1/3. And my second row, I did not do anything to it, so it's still a 5, a 2, and a 19. So step 1 is done. I have obtained a 1 in my first column, first row. So I need to use that and somehow manipulate that in such a way that I can turn this 5 on the next row into a 0. Well, if I took row 1 and multiplied row 1 by negative 5, so I'm just going to document this right here. I'm going to take row 1 and multiply it by negative 5. I'm going to write it right on top of this, so just kind of hang on here what's going on. If I take that negative 5 times 1, I get negative 5. If I take negative 5 times negative 4/3, I get positive 20/3. And if I take negative 5 times 1/3, I get negative 5/3. And so what I've written there in blue is the exact same line as row 1. It just looks a little different because I multiplied it by that scalar. And if you remember, that is a legal move. And I bumped something and it's moved on. Sorry about that. Okay, so now that I've done that, I am going to do some combining. First of all, I'm going to leave row 1 alone. So row 1 I did not change. I mean, yes, I wrote those numbers in blue, but I'm going to use those when I combine with what row 2 is. So as of right now, I'm leaving row 1 alone because it has what I want. It's got a 1 in that first column, first row. And here's my negative 4/3. Here's my 1/3. Okay, now if I combine, because it said that it's legal with matrices to combine a multiple of one row with another row to replace that row. So if I take, and I'll write it down right here, if I take row 2 and add to it negative 5 row 1s. So that's what's happening here. I took row 1 and multiplied it by negative 5, and I'm going to combine these blue numbers for row 1 with my original row 2. So negative 5 and positive 5. Well, negative 5 and positive 5, that combines to 0. The next one, I have 20/3 and 2. Let's see, 20/3 and 2. Well, 2 is the same thing as 6/3, right? So 6 divided by 3 is 2. So 20/3 and 6/3, combine those, that would give me 26/3. And then negative 5/3 and 19. Well, 19 would be 57/3, because 57 divided by 3 is 19. So 57/3 combined with 5/3 would be 52/3. Okay, So as we move along here, I do now have row 1, column 1 is a 1, and every other number in column 1 is now a 0. And so now I need to somehow turn 26 thirds into a 1. Well, 26 thirds is a fraction. How do you turn a fraction into a 1? Well, you multiply that fraction by the reciprocal. So what I'm going to do here is I'm going to take the reciprocal of 26 thirds, which is 3/26. Now I know it's ugly, but we're going to do it anyway. So I'm going to multiply row 2 by 3/26. All right. So I haven't done anything to row 1, so I'm just going to keep row 1. 1, -4 thirds, and 1/3. Now row 2 is being multiplied by 3/26. Well, 3/26 times 0 is just 0. 3/26 times 26 thirds, the 3's cancel, the 26 cancels, leaving me 1 over 1, so that's 1. 3/26 times 52, well, the 3's cancel. If the 3's cancel, I'm left with 52 over 26. Well, 52 divided by 26 is 2, so that's just a 2. And I now have row 2, column 2 has a 1 in it. I'm going to use that 1 to get rid of the -4 thirds. Well, to turn a -4 thirds into a 0, I need a +4 thirds. So to turn a 1 into 4 thirds, I'm going to multiply row 2 by 4 thirds. I'm just going to write it just like I did before. I'm going to write it in blue here. Well, 4 thirds times 0 is still 0. 4 thirds times 1 is 4 thirds. And 4 thirds times 2 is 8 thirds. And so now that I've done that, I'm going to combine. I'm going to take row 1, and I'm going to add 4 thirds of row 2, and I'm going to put that in place of row 1. So again, so here's my row 1 is 1, -4 thirds, and 1/3. I'm going to combine that with what I wrote down here in blue, where I took row 2 and multiplied it by 4 thirds. So 1 plus 0 is 1. -4 thirds plus 4 thirds is 0. 1/3 plus 8 thirds, well, 1/3 plus 8 thirds is 9 thirds, but 9 thirds, that's 9 divided by 3. 9 divided by 3 is 3. And I didn't do anything in my second row, so I'm just going to keep it. My second row is 0, 1, 2. Okay, I have now solved this system of equations. Remember that column 1 represents my x's, and column 2 represents my y's. So what this first line is, I've got this 103 on the first my first row. That 103 means that 1x plus 0y equals 3. So basically, looking at that first row, I know that x equals 3. On row 2, I have a 0, a 1, and a 2. Well, what that means is 0x plus 1y equals 2. Well, all that's telling me is that y is equal to 2. And so by using this Gauss-Jordan method in making this, this major diagonal of 1s and everything else 0s, I have made the 3 and the 2 become the solution of the system. So the answer to the system of equations, mosquito, the answer to the system is my x value is 3 and my y value is 2. So the answer, the solution to this system is 3, 2. Okay. And again, that solution is read directly from that column right there. The answer is 3, 2. Okay? And so that's just a simple, 2 variables, 2 equations, solving that. But what if the equation gets bigger? Say 3 equations and 3 unknowns. Well, we can apply the exact same process here. It's just going to involve a lot more steps. Okay? So let's go ahead and do this one. First of all, we have to make sure are my variables lined up? Yes, I have a column of x's, I have a column of y's, I have a column of z's, my equal signs are all lined up, and my solutions are all lined up. So we're good to go there. So now that it's lined up and ready to go, we'll start putting this together. We'll start by writing the coefficient matrix. And again, coefficient matrix means let's ignore the variables, ignore the equal sign, and let's make this matrix. So the first equation. The x coefficient is 1, the y coefficient is -1, the z coefficient is 5, and I have a solution of -6. Equation 2, x coefficient is 3, y coefficient is 3, z coefficient is -1, with a solution of 10. And the third equation, x coefficient is 1, y coefficient is 3, z coefficient is 2, with a solution of 5. There's my matrix. If you want to show the augmented by separating the coefficient matrix from the solution matrix, you can draw that line, but again, that's not necessary. Okay, going back to following the steps. Step number 1 to solving is to make row 1, column 1, a 1. And if I look at this, if you'll notice, look there, it's already a 1. It's good to go. So I don't need to do anything to make row 1, column 1, a 1. But I need to use that 1 to make the 3 go away and the 1 go away. So let's just we'll do it both of them in one shot, but how do I take a 1 and make a 3 go away? Well, to make that 3 go away, I need a -3. So what I will do is I will take row 1 and multiply it by -3. Okay? So -3 times 1 is -3. -3 times -1 is +3. -3 times 5 is -15. And -3 times -6 is +18. So I'm going to take row 2 and subtract 3 row 1s. All right, so I'm not going to do anything to row 1. I'm going to go ahead and write it down. Row 1 is still 1, -1, 5, -6. If I take row 2 and subtract 3 row 1s, basically what I'm doing here is taking this 3, 3, -1, and 10, and I'm going to combine it with my green when I multiplied row 1 by -3. So if I combine 3 and -3, I get a 0. If I combine 3 and 3, I get a 6. If I combine -1 and -15, I get -16. And if I combine 10 and 18, I get a 28. So I have replaced row 2 with row 2 minus 3 row 1s. And you'll notice I now have a 0 in row 2, column 1, which is what I want. I now need to turn row 3. I need to turn that 1 into a 0. So to do that, I'm going to take row 1, because again, that's the equation that I'm using to turn other things into 0. I'm going to take equation 1 and just multiply it by -1. That gives me a -1. -1 times -1 is 1. -1 times 5 is-5. -1 times -6 is 6. So I'm going to replace row 3 with the sum of row 3 minus row 1. So I'm going to take the row 3 that I see here, the 1, 3, 2, 5, and I'm going to combine it with what I wrote in red up here for row 1. So 1 and negative 1 give me 0. 3 and 1 give me 4. 2 and negative 5 give me negative 3. 5 and 6 give me 11. Okay. Okay, so now I've got this new matrix that I'm working with. I have a 1 in the first column and in the first row, and everything else in column 1 is a 0, so I'm good to go there. So now I'm going to start working with row 2. So I want to turn this 6 into a 1. Well, to do that, all I'm going to do is multiply all of row 2 by 1/6. Okay, so if all I'm doing is multiplying, let's see, I'm going to take 1/6 of row 2. Okay, so if I'm taking 1/6 of row 2, I'm not doing anything with row 1, so I'm just going to keep him. 1, negative 1, 5, negative 6. But I'm taking 1/6 of row 2. 1/6 of 0 is 0. 1/6 of 6, well, that'd be 6 divided by 6, that's 1. 1/6 of negative 16, that would be negative 16 divided by 6. Well, negative 16 divided by 6 reduces to negative 8/3. And 1/6 of 28, that would be 28 divided by 6. 28 divided by 6 would be 14/3. And I have not done anything to row 3, so I'm just going to keep row 3 as it is. Okay? And I have successfully made row 2, column 2, a 1. I'm now going to use that second row to get rid of the numbers that are not 0 in both row 1 and row 3. Okay. Well, if you'll notice, if I combine row 1 and row 2 just like they are, that negative 1 in row 1 will be gone. So I don't have to do anything special with row 2 to fix row 1. So I'm just going to take row 1 and add to it row 2. Well, 0 plus 1 is 1. Negative 1 plus 1 is 0. 5 minus 8/3, well, let's see, 5 would be, what, 15/3? And 15/3, because 15 divided by 3 is 5, 15 minus 8 is 7, so that would be 7/3. And then we have 14/3, and here's a negative 6. Well, negative 6 would be what, negative 18/3, because negative 18 divided by 3 is negative 6. Negative 18/3 combined with a positive 14/3 would be a negative 4/3. I'm not doing anything with row 2 right now, so I'm just going to keep it. 0, 1, negative 8/3, and 14/3. And I want to get rid of this 4 in row 3. So to get rid of the 4, I need a negative 4. So if I took row 2 and multiplied it by negative 4, negative 4 times 0 is 0. Negative 4 times 1 is negative 4. Negative 4 times negative 8 thirds would be a positive 32 thirds. And negative 4 times 14 would be negative 56 thirds. So now, to get rid of the 4 in row 3, I'm going to take row 3, and I'm going to subtract 4 row 2's, or add negative 4 times row 2, same thing. Okay, so combining row 3 with my red row 2, 0 and 0 is 0. Negative 4 and 4 is 0. 32 thirds minus 3 thirds, 32 thirds minus 3, well 3 would be, this would be a negative 9 thirds. So 32 minus 9 would be 23. So negative 23 thirds, a positive 23 thirds. And we have a negative 56 thirds and 11. Well, 11 is the same thing as 33 thirds. And a negative 56 plus 33 thirds would be 23 thirds. Negative. Okay. And there you go. Moving right along. So now we have row 1, column 1 is a 1. Everything else in column 1 is a 0. Row 2, column 2 is a 1. Everything else in column 2 is a 0. And now we need to work with that last one. Row 3 is pretty ugly right now, but I want to turn that 23 thirds into a 1, so all I have to do is multiply that by the reciprocal. So all I'm going to do now is I'm going to take 3 23rds of row 3. Okay, so I haven't touched row 1 on this step, so I have 1, 0, 7 thirds, negative 4 thirds. I haven't touched row 2, 0, 1, negative 8 thirds, 14 thirds. I did touch row 3 because I'm taking row 3 and multiplying it by the reciprocal of 23 thirds. So that's going to give me 0, 0, 1, negative 1. And so now I have my 1's on my diagonal, so I'm getting really, really close to the answer. The only thing I have left to do is I need to get rid of the 7 thirds in row 1. I need to get rid of the negative 8 thirds in row 2. So to do that, we're going to have to do a little bit more math. So to get rid of the 7 thirds in row 1, I need to turn the 1 in the bottom into a negative 7 thirds. Well, that means I'm just going to take that row 3 and multiply it by negative 7 thirds. Negative 7 thirds. Well, negative 7 thirds times 0 is 0, 0. Negative 7 thirds times 1 is negative 7 thirds. And negative 7 thirds times negative 1 is positive 7 thirds. So row 1 is now being replaced. I'm going to take row 1 and subtract 7 thirds of row 3. And again, that just means take row 1 and combine it with my green row 3 here. Well, 1 and 0, that's 1. 0 and 0, that's 0. 7 thirds and negative 7 thirds, that's 0. Negative 4 thirds and positive 7 thirds, that gives me a positive 3 thirds. Well, positive 3 thirds is 1. So row 1 is good. In row 2, I need to get rid of a negative 8/3. Well, to get rid of the negative 8/3, I need a positive 8/3. So I'm going to multiply row 3 by 8/3. 8/3 times 0 is 0. 8/3 times 0 is 0. 8/3 times 1 is 8/3. 8/3 times negative 1 is negative 8/3. Let me go ahead and write down, oops, leave it in red. Okay, so my row 2 is going to be replaced by taking row 2 and adding 8/3 of row 3. So I'm going to take my row 2 here that's in blue and combine it with my red row 3 down here. So 0 and 0 is 0. 1 and 0 is 1. Negative 8/3 and positive 8/3 is 0. 14/3 minus 8/3. 14/3 minus 8/3 is 6/3. And 6 divided by 3, of course, would be 2. And I did not do anything to row 3. So I'm going to write down my original blue row 3 here, move it forward. I have a 0, 0, 1, negative 1. Make that my augmented matrix. I have a diagonal of 1s on the left side with everything else being 0. And on the left side, I have my answers, x, y, and z in order. So x is 1, y is 2, z is negative 1. You know, when we're solving a system of lines on a plane, we just have an x and a y, and we call that an ordered pair. This is not an ordered pair because there's 3 of them. And so mathematicians are super, super geniuses when they name things. So instead of calling this an ordered pair because it's 3, we're going to call it an ordered triple. Okay, so we have an ordered triple as an answer. So what we've done there is we now have the solution to this system of 3 variables and 3 unknowns. So I started with this system right here, and once I get done, I know that x is 1, y is 2, and z is negative 1. Use the Gauss-Jordan to solve this system. All right, so we're back to a 2 by 3. Remember, 2 rows by 3 columns. So we will write our matrix equation, or our augmented matrix. Our augmented matrix coefficients are 1, 1, 2, 2, 2, 5. Okay, so again, step number 1, row 1, column 1, make it a 1. Hey, we're done. Now I'm going to use this 1 to get rid of the 2. So I'm not doing anything to row 1. Row 1 is still 1, 1, 2. How do I get rid of that 2 in column 1, row 1? To get rid of that 2 in row 1, column 2, I'm sorry, row 2, column 1, to get rid of that 2, I need a negative 2 up at the top. So I'm going to take a negative 2 and multiply row 1 by negative 2. Doing so, negative 2 times 1 is negative 2. Negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. Okay. So I'm going to replace row 2 by taking row 2 and subtracting 2 row 1s from it. So I'm taking that row 2 and combining it with how I rewrote row 1 in red. 2 minus 2 is 0. 2 minus 2 is 0. And 5 minus 4 is 1. And so now, row 1, column 1 is a 1, everything else is a 0. I need to make row 2, column 2, a 1. And folks, there is nothing that I can multiply that 0 by to get a 1. So I have a slight problem here. Wow. Let's think about that second row. Remember when I wrote x plus y equals 2, let me arrow it this way. When I wrote x plus y equals 2 in my matrix, I wrote it as 1, 1, 2, right? Because that's 1x plus 1y equals 2. Well, let's take a look at what just happened. When I did my Gauss-Jordan, this second row here, let's write what that means. What I'm just telling you right here with that 0, 0, 1 is I'm telling you that 0x plus 0y equals 1. Well, if I have 0 x's, that means I have nothing. If I have 0 y's, that means I have nothing. And if I have nothing plus nothing, I still have nothing. So this line right here is telling me that, that 0 is equal to 1. And hopefully you don't appreciate that. That's definitely not true. Okay? So when you're doing this Gauss-Jordan method, if you have your left side all zeros and a number that's not 0 on the right side, that's a false statement. That can't happen. So what happens here is this system has no solution. Of course, you can also write that as a 0 with a line through it, like so. Okay, but yeah, this system has no solution. 0 does not equal 1. It didn't in the past, and it's not in the future, and it doesn't now. So yeah, we're done with this problem. Use the Gauss-Jordan method to solve the system. Write the solution set with z arbitrary. Okay, so here's the deal. If I need to solve for 3 variables, I have to have 3 equations. This is only 2. You can't solve for 3 variables with only 2 equations. So because of that, this is going to be very arbitrary as far as our answers go. So let's start off just like we're doing our Gauss-Jordan. We have 2 equations, so we have 2 rows. But we have 4 columns. So this is going to be a 2 by 4 matrix. Okay, so let's go ahead and start off by writing our augmented matrix. Our coefficients are 2, -5, 3, and 1. Row 2, 1, -2, -2, and 8. Okay. So step 1 is to somehow make row 1, column 1 a 1, and it's right now a 2. Well, I could, if I wanted to, multiply all of line 1 by a 1/2 and turn that 2 into a 1. But if you'll notice, I've already got a 1 right here. So what I'm going to do is I'm just going to simply swap these guys. So I'm going to write row 2 on the top and row 1 on the bottom. And when I do that, I have 1, -2, -2, 8. And row 1 goes on the bottom now, 2, -5, 3, 1. Okay, so now row 1, column 1 is a 1, just like I want. I now want to use that 1 and turn the 2 into a 0. Well, to do that, to get rid of a 2, I need a -2. Well, to turn a 1 into a -2, I'm going to multiply row 1 by -2. -2 times 1 is -2. -2 times -2 is 4. -2 times -2 is 4. -2 times 8 is -16. So now, my new row 2, which was 2, -5, 3, and 1, I'm going to take row 2 and subtract 2 row 1s from it. Now remember, I've changed the names of my rows. So 1, -2, -2, 8 is now row 1, and 2, -5, 3, 1 is now row 2. Okay? Well, I'm changing my new row 2, which means row 1 hasn't changed. It's still 1, -2, -2, 8. But my new row 2 is the combination of this row 2 of 2, -5, 3, and 1 combined with my red row 1 up there. So 2 and -2 give me 0. -5 and 4 give me -1. 3 and 4 give me 7. 1 and -16 give me -15. Okay? Well, now I need to make row 2, column 2. I need to turn that -1 into a positive 1. And that's done simply by multiplying row 2 by -1. So row 1's not changing at all. Row 1 is still 1, -2, -2, 8. And I'm going to take -1 row 2's. So basically change the signs on row 2. That gives me 0, 1, -7, 15. Okay. I've got a 1 in row 1, column 1, everything else zeros. In row 2, column 2, I have a 1. I need to turn that -2 into a 0. Well, to turn a -2 into a 0, I need a positive 2. So I'm going to take row 2 and multiply it by 2. 2 times 0 is 0. 2 times 1 is 2. 2 times -7 is -14. 2 times 15 is 30. I'm now going to take row 2 and add, back this up. Row 1's being replaced. So I'm going to take row 1 and add 2 row 2's to it. So take row 1, add it to my green row. 1 and 0 is 1. -2 and 2 is 0. -2 and -14 is -16. 8 and 30 is 38. Row 2 has not changed. 0, 1, -7, 15. Okay, so if you'll notice here, what's happened is my main diagonal, starting with the top left, is a 1. Everything else is a 0. My next one in the diagonal is a 1. Everything else is 0. And if you'll notice, I can't go any further. Okay, so I still have, this first row has an X and a Z in it. The second row has a Y and some Z's in it. Okay, and I can't go any further than that with the Gauss-Jordan method. So that first equation tells me that X minus 16Z equals 38. And that second row tells me that Y minus 7Z is equal to 15. So those are my two equations written both in terms of X, Y's, and Z's. Now the original problem told us write the solution set with Z arbitrary. So the answer is going to still include Z in it. So what does X equal? So if I got X by itself, I would have to add 16Z to both sides. So X is equal to 16Z plus 38, and Y is equal to 7z, because we have to add 7z to both sides, plus 15. So that's the value of x and the value of y. And what's z? Well, z is just z. Z is arbitrary, okay? I can't solve this system, but if you give me a value for z, I can give you some more numbers that make it work. That's what that's saying. So to write we have to write this answer as an ordered triple, just like we did on the previous problem. So let me go back real quick. On the previous problem, this was no solution. One more, back one more. So on this system here, we found x to be 1, y to be 2, and z to be -1. So we wrote that as an ordered triple. And guys, we're going to do the exact same thing with this arbitrary system. I can still write this as an ordered triple. So ordered triple is going to go in parentheses. My x value is 16z plus 38. My y value is 7z plus 15. And my z value is z. So this here is my ordered triple. So that is my answer with an arbitrary z. Okay, so just a summary of what could happen when you're solving systems. When matrix methods are used to solve a system of linear equations and the resulting matrix is written in diagonal form or as close as possible to diagonal form, obviously that last one was not quite diagonal form, but it was close. There's three possible scenarios. Number one, if the number of rows with non-zero elements to the left of the vertical line is equal to the number of variables in the system, then the system has a single solution. Possibility number two, if one of the rows has the form 0, 0, 0, and then some number on the constant side when a is not 0, then the system has no solution. Number three, if there are fewer rows in the matrix containing non-zero elements than the number of variables, then the system has either no solution or infinitely many solutions. If there are infinitely many solutions, you have to give the solutions in terms of one or more arbitrary variables. All right? So that wraps up 5.2. Go back and watch this video. If you need to watch any of it again, pause it as you're taking notes. If you have any questions, you feel free to contact me via Canvas or email or drop a message on the YouTube video. Be more than happy to help you out. Good luck to y'all. Y'all have a great day.